Let's look at the third question. Have a close look. And yeah, I have an x by 4. We'll avoid that one, but let's look at number 3. 3a. So let's calculate the change in entropy when 100 kilojoules of energy is transferred reversibly, isothermally, as heat to a large block of copper at 0 degrees Celsius and 50 degrees Celsius. So let's extract out the given from that question. This is the third exercise, the end of chapter 3. And let's see what we have. I just read it. Let's look at it again. So we have a copper block. "100 kilojoules of energy is transferred reversibly and isothermally as heat to a large." So I have Q going to this, and Q is equal to then a positive value, 100 kilojoules. Energy transferred reversibly and isothermally. So reversibly, and delta T is 0. Isothermally. So I have an isothermal transfer of Q, which sounds a little strange, but that's okay, to a large block of copper. And I think that's the key word there, that it's a large block at 0 degrees Celsius and then at 50 degrees Celsius. So there's really two things. We'll do them one at a time. So it's done first at 0 and it's done secondly at 50 degrees Celsius. So we want to compare. And we want to find delta S in each case. Are they the same? Are they different? Which one's larger? And that's what you want to get out of this question, okay? So yes, it's an exercise, but we want to know, we want to be able to determine what would have the greater change or the smaller change in entropy. It's the same amount of Q being transferred, but it's being transferred at different temperatures. And so is it only related to the amount of Q that's being transferred or not? So I said the word big, the big block, is important, it's significant in this question, and that's to rationalize how can it not be changing temperature. And that's because I've got overall not a change in temperature in this large copper block because the heat is being transferred to it, but it's large enough to actually stay at that temperature. Okay, so how do I determine my delta S? Well, ds is equal to dq reversible over temperature. And I think I'm ready to just integrate this expression to get delta S. So if I take this and I integrate, the temperature is constant, and so I do have that delta S is equal to the Q reversible over temperature. And so let's take this and apply it to the first case where it is 0. That was 100 kilojoules. 100 kilojoules, so that's 100,000 joules. It was transferred to the copper, so I maintain that positive sign. And the temperature is 0 plus 273.15 Kelvin. And when I calculate that, I get an answer of 366 joule per Kelvin. So I think you see where this is going. If I have the same value on top, 100,000 joules, now this time on the bottom, I'm converting from 50 degrees Celsius plus 273.15 Kelvin. So I have a larger number on the denominator. That's going to, looking at my calculator, so that's going to be 309 joule per Kelvin. So because it's larger, I suspected that it was going to be a smaller value. And so the change in entropy, if I start at 0 and I transfer that value of Q, I have a change in entropy of 366 joule per Kelvin. But if I start at a higher temperature, I actually have a smaller change in entropy that results. So the takeaway from this question, of course it's straightforward, so it's not a real test of your skills in that respect, because it's a bit of a plug and chug question. But think about if you were just asked in a qualitative way, which of these two situations would lead to a larger change in entropy and why? Which of the two initial temperatures, a higher or lower with the same value of Q, would involve a larger or smaller entropy change, but the key is and why. And then you would say, well, let's do two examples, and this would demonstrate. Okay? Great. So that's question number 3. Let's have a look at, so 4 we were scrapping. I've done it, but I don't really like the idea behind it, so let's skip to 5. And so for 5, calculate the change in entropy when 15 grams of carbon dioxide gas is allowed to expand from 1 to 3 liters. It's isothermal at 300 Kelvin. So let's take all that information. You can, for example, after watching this video, maybe try the accompanying question, the B part, and see how you do there, because they're often really quite similar. So here we go for 5, and we'll sneak this one in on the video and then stop it after 5. So I have CO2 gas. I have 15 grams of that. And yeah, the initial volume is 1 liter or 1.0 decimeter cubed is what's written. And it's at 300 Kelvin. It'll undergo isothermal expansion, so delta T is equal to 0. There we go. And all I know about the end is that it's at 3, well, I know it's not only 3 liters, but also 300 Kelvin still. And again, I want to find delta S. So I'm going to start at thermodynamic definition, the reversible Q over temperature. What will we do? If I integrate that right away, I have that delta S is equal to, it's isothermal, so that's why I think I can do it right away, because my temperature is constant. So dq integrates to just Q, reversible, and temperature is constant. So I have this. I don't have the Q, but this is an isothermal expansion and of a gas. I do have the 2 volumes. So because it is isothermal, delta U is equal to 0, and therefore my Q reversible is equal to the negative value of the reversible work or maximum work, and that is equal to, now just never mind this negative sign for the moment, because work, I'm trying to cover it, work is equal to minus nRT ln V final over V initial, so the negative value then of the work is equal to positive nRT ln V final over V initial. So this is what I have for the Q reversible, and although I do know what the temperature is, it's interesting that I don't need to know what the temperature is for delta S calculation. Because look, I'm going to put this in for, I'm really going to press this point here because it is a tutorial, sort of, and divide by temperature. Okay, so interesting that the change in entropy for an isothermal expansion is independent of the temperature. See how we can get statements out of this? So you want to be thinking about what bigger question statements come out of these exercises when you do them. So nR ln V final over V initial. So I have to calculate N here and get my calculator. So why don't you go ahead and do that. And I will as well. 4 2 equals plus so my delta S is equal to my number of moles. It is, I thought it was 15. Yeah, it's 15 grams. 15 grams of CO2 times 1 mole of CO2 is, I'm going to use 44 grams because this is just to 2 sig figs as well. What value of R are you going to use here? I have two choices, the 0.08206 liter atmosphere per mole Kelvin or the 8.3145 joule per K mole. And then I have the ln of the V final over V initial, and that's basically the ln of 3, because it's 3.0 liters, 1.0 liters. Make sure you cross those out because we really should just take the ln, not just really, we can only take the ln of the number. And I'm going to cross out my units here, and I see that my units are joule per Kelvin. So delta S is, can you see? Yeah. 15 divided by 44 times 8.3145. Multiply, and then I'll just open the bracket. 3 ln close bracket equals, and I have 3.11 joule per K. Seems really small. I'm just gonna check that. Yeah, no, that's it. 3.11 joule per Kelvin. Does it make sense that it's that small? Got a really small amount of carbon dioxide, and it's not expanding too greatly. So there you have it. So that's the that is the answer for question 5. So let's stop it there. Pick it up for the next couple.